Welcome to solverfy.
Hello there. In this exercise we have here first the set of Pauli matrices. So the matrices are labeled by the letter sigma. So sigma 1 is this matrix 0, 1, 1, 0, sigma 2 is 0 minus I 0, and sigma 3 is 1, 0, 0 minus 1. So these are called the Pauli spin matrices, but I'm just calling Pauli matrices. And there is another set of matrices that are important that are formed like block matrices here that depend on the Pauli matrices. So you can observe here we have the matrix beta that is equals to the identity. Here the identity, this is a block matrix formed by the identity 2 by 2, the 0 matrix 2 by 2, 0 matrix 2 by 2, and here minus the identity of minus the identity matrix 2 by 2. And then we have the other direct matrices, alpha x, that has the sigma 1 Pauli matrix, alpha 2 has sigma 2, and alpha z has the sigma 3. Okay, so I'm going to abuse a little bit here. I'm going to change the notation to make the things easier. So I'm going to call it this, instead of alpha x, alpha 1, this alpha 2 and alpha 3, to make the calculations easier. So the first thing that we need to show is that the square of all the direct matrices are the same. Alpha 1, alpha 2 square, alpha 3 square. All these matrices, the square of each of these matrices are the same. Okay, so in order to do this, let's remember that the Pauli matrices follow some properties. Okay, so technically if we take two Pauli matrices, let's say sigma I and sigma I, this is going to return us the identity matrix 2 by 2 for all I from 1 to 3. Okay, so that means that if we take two Pauli matrices and then multiply by itself, we are going to obtain the identity matrix. Or this can be written also as sigma I square is equals to the identity matrix 2 by 2. And what other property these Pauli matrices satisfy? Well, if we take two different Pauli matrices, they satisfy the property that they are anti-commutative. That means that the multiplication of sigma I with sigma j is equals to minus sigma j sigma I. Okay, for all I different from j, and of course I and j goes take values of 1, 2, and 3. Okay, so having in mind these properties that has the Pauli matrices, we can infer the properties of the Dirac matrices. So look that for the beta matrix, this is trivial. If we multiply twice, this matrix corresponds to multiply the following matrix with itself. Here we have the identity matrix 2 by 2, the 0 block, and minus the identity. This multiplication will result in the identity of 4 by 4. Okay, because if we multiply this block with this block, here is the identity matrix, and this block with this block will be the positive identity matrix 2 by 2. If we have two block matrices of 2 by 2 in the diagonal part, that means that we have just the identity matrix 4 by 4. So we need to show that for all the for the rest of the Dirac matrices, this is true. So let's remember that I put here a label as alpha I. So alpha I is the matrix that is equals to 0, sigma I, 0. Okay, so what happens if we multiply alpha I with itself? Or in other words, we take alpha I squared. This is going to be equal to sigma I squared 0, 0 and sigma I squared. And we know that the sigmas, this sigma, these polymatrices, if we take the square, that it will return as the identity matrix 2 by 2. So that means that this will result into the identity matrix 2 by 2, 0, 0. Here the identity matrix 2 by 2. But this is no more than the identity matrix 4 by 4. And this is satisfied for all the i's from 1, 2, and 3. Okay, so that means that for all, well, that alpha 1 squared is equals to alpha 2 squared, that is equals to alpha 3 squared, that is equals to beta squared, and all of them are equals to the identity matrix. And now we need to show the anti-commutativity property of the Pauli of the Dirac matrices. Okay, so that's the part B. We need to show that the Dirac matrices satisfy this property. We have two matrices A and B. There, the multiplication is equals to minus BA. Okay, and we know that the Pauli matrices satisfy this property, because if we take sigma I and sigma j, this is equals to minus sigma j sigma I for all the values I different from j, and clearly ij can take values of 1, 2, and 3. Okay? So let's look what happened with the Dirac matrices. So I'm going to use the notation, similar notation. We need to show that alpha I, alpha j is equals to minus alpha j, alpha I. So let's take first the left hand side of this expression. Alpha I, alpha j is equal to the matrix sigma I, sigma j, 0, 0, and here sigma I, sigma j. Okay? And if we use this property here of the Pauli matrices, this is going to be equal to the matrix minus sigma j, sigma I, 0, 0, sigma j, sigma I. Okay? And now let's take the right hand side of this equation. So the right hand side is minus alpha j, alpha I, but this is equals to minus the matrix sigma j, sigma I, 0, 0, sigma j, sigma I. And you can see that these two matrices are the same. So these, all the Pauli matrices, okay, and I forgot to mention that this holds for all the I different from j, and I and j of course take values from 1, 2, and 3. Okay, so that means that indeed the Dirac matrices are anti-commutative.